No matter how much we learn about the universe, there are still many existential questions. It's impossible to tell if the universe is finite or infinite. We just know its physical size can't be as big as we can see. We don't know if our universe contains everything or if it's one of many. Due to the lack of evidence, we don't know what happened in the first fraction of a second of the Big Bang. But we're sure the universe has an edge, not in space but in time. Because the hot Big Bang occurred 13.8 billion years ago with an uncertainty of less than 1%, we can only see so far. It's hard to see as far back as we can even at the speed of light, the limit of the cosmos. The farther away we look, the farther back in time we can see. So here's what we see from the edge of the universe. Welcome to Space Discoveries. Subscribe to the channel for every single detail about the new discoveries in the vastness of the space. Also, do not forget to hit that bell icon for new updates. Having said that, let's get started. Our universe today is what it has become after 13.8 billion years since the hot Big Bang. In the universe, most galaxies are clumped together in galactic groups, like the Local Group, and rich clusters, like the Virgo cluster, separated by enormous voids of mostly empty space. These galaxies are a mix of spirals and ellipticals, where a typical Milky Way galaxy forms about one new sun-like star per year. In addition, most of the normal matter in the universe is hydrogen and helium, but about 1 to 2% of it is heavier elements from the periodic table, allowing for rocky planets like Earth and complex chemistry. Even though there is a lot of variety, some galaxies form stars, some have active black holes, others haven't made any stars for billions of years, etc. The galaxies we see are large, evolved, and clumped together on average. As we look farther and farther away, we see how this universe grew into what it is today. When we look at the universe at a greater distance, we notice it's slightly less clumpy and more uniform, especially at larger distances. We see that galaxies are lower in mass and less evolved. There are more spirals and fewer elliptical galaxies. On average, there are more bluer stars, and the star formation rate used to be higher. There's less space between galaxies, but the mass of groups and clusters is smaller. In other words, our modern galaxies are the result of smaller, lower-mass galaxies merging together over cosmic timescales, building themselves up into the massive behemoths we see around us. The universe, at earlier times, consists of galaxies that are physically smaller, lower in mass, closer together, larger in number, bluer in color, richer in gas, with higher rates of star formation, and with fewer proportions of heavier elements as compared to today's galaxies. But as we go further and further away to earlier and earlier times, this gradually changing picture starts to shift abruptly. Looking back 19 billion light-years, we see that star formation reached its peak when only 3 billion years had passed since the hot Big Bang, about 20 to 30 times the rate at which new stars are formed today. Currently, a great majority of supermassive black holes are emitted enormous quantities of particles and radiation due to the consumption of surrounding matter. Over the past 11 billion years, the universe's evolution has slowed down. Yes, gravity keeps crashing structures, but dark energy kicks in and dominates the universe's expansion more than 6 billion years ago. We're still forming stars, but the peak of star formation is far behind us. And supermassive black holes keep growing, but they shone brightest earlier, with more of them faint and inactive now than during those early days. As we get closer to the edge defined by the hot Big Bang, we start to see even more drastic changes. When we look at distances of 19 billion light-years back in time, that's when the universe was just 3 billion years old, star formation was at its peak, and the universe was maybe 0.3 to 0.5% heavy elements. But as we get closer to 27 billion light-years away, the universe was only 1 billion years old. Star formation was much smaller, with new stars forming at nearly a quarter of what they'd be later on. As time goes on, the amount of normal matter that's heavy elements plummets to 0.1% at an age of 1 billion years, and to just 0.01% at around 500 million years. In those early environments, rocky planets may not have been possible. There was not only a significantly hotter cosmic microwave background, it would have been infrared instead of microwave, but every galaxy in the universe would also be young and full of young stars. They're not likely to be elliptical galaxies yet. Beyond that, our current instrumentation just can't keep up, but telescopes like Keck, Spitzer, and Hubble have already started to. When we get to distances of roughly 29 billion light-years, which corresponds to times when the universe was 700 to 800 million years old, we start to run into the first edge of the universe, the edge of transparency. Currently, we assume that space is transparent to visible light, but that's only true because it isn't full of light-blocking materials like dust or neutral gases. In the beginning, before enough stars formed, the universe was full of neutral gas and hadn't been fully ionized by the ultraviolet radiation from these stars. Therefore, a lot of the light we see is obscured by these neutral atoms, and the universe becomes reionized only once it's formed enough stars. That's why infrared telescopes, like NASA's James Webb, are so important to study the early universe. There's an edge to where we can see in wavelengths we're used to. A distance of 31 billion light-years, corresponding to just 550 million years after the Big Bang, is when we reach the edge of reionization, where most of the universe is transparent. Reionization is a gradual process and takes place unevenly. It's like a jagged, porous wall in a lot of ways. It happens sooner in some places, which is how Hubble spotted its most distant galaxy so far, at 32 billion light-years away, only 407 million years after the Big Bang. But it doesn't happen completely in other parts until almost a billion years have passed. Still, beyond the limits of our current instrumentation, stars and galaxies must certainly have existed. Even the farthest galaxies we've found show evidence of previous generations of stars living inside, and they're pretty bright and massive. Even beyond the limits of what our current telescopes can see, however, we can still see indirect signs of stars forming. The emission of light by hydrogen atoms themselves, which happens only when stars form, ionization occurs, and then the free electrons recombine with ionized nuclei, releasing light as a result. Currently, all we have are indirect signs of early star formation, saying that young galaxies existed 180 to 260 million years after the Big Bang. These proto-galaxies formed so many stars. We can see the first hints of their existence buried in the data, which corresponds to a distance between 34 and 36 billion light-years away. Even though our current telescopes can't see these galaxies, many astronomers hope James Webb can. Recent discoveries give us a good example, but we'll get to that later. However, there are probably still sources of light going back even earlier and the first ionized regions in the universe. Those first stars, if we could see back that far, are expected to come about between 38 and 40 billion light-years away, which corresponds to times just 50 to 100 million years after the Big Bang. Before that, the universe was only dark, full of neutral atoms and radiation from the Big Bang's leftover glow. Even further back, there are other edges of interest. In 44 billion light-years, the radiation from the Big Bang is hot enough to be visible. If a human eye existed, it would see the radiation start to glow red, like a red-hot surface. This corresponds to a time just 3 million years after the Big Bang. When we look back 45.4 billion years, we find a time just 380,000 years after the Big Bang, when it gets too hot to keep neutral atoms in place. From here comes the cosmic microwave background, the leftover glow of the Big Bang. If you've ever seen that famous picture of the hot red and cold blue spots from the Planck satellite below, this is where that radiation originates. And before all that, 46 billion light-years away, is the ultra-energetic state of the hot Big Bang, where atomic nuclei, protons, neutrons, and even the first stable forms of matter were formed. During these stages, everything can only be described as cosmic, primordial soup, where every particle and antiparticle in existence has been created from pure energy. But what's beyond this high-energy soup is still a mystery. We don't know what happened in those earliest stages, although many predictions of cosmic inflation have been indirectly confirmed. We see back 13.8 billion years in all directions at the edge of the universe, but that depends on the observer's position in space-time. There are many edges to the universe: the edge of transparency, the edge of stars and galaxies, the edge of neutral atoms, and the edge of our cosmic horizon from the Big Bang. Although our telescopes can take us as far as they can, there will always be a limit. Although space itself is infinite, the time since the Big Bang isn't. No matter how long we wait, there's always going to be an edge we'll never get past. And that's it for now. Thank you for watching the video. If you liked the video, then don't forget to press that thumbs up button and also that hot red subscribe button. And we'll see you in the next video.